Hey everyone, welcome to the 3-3 notes, special segments in triangles. So today we're going to talk about medians, altitude, angle bisectors, and perpendicular bisectors. There's not going to be many computational problems here. It's a lot of just definitions. I'm going to draw them. I'm going to explain to you how these segments are formed, their properties, and things of that nature. So the first of these types of segments that we're going to discuss is a median. Now a median is a segment that connects a vertex, so that's very important to know that it connects the vertex to the midpoint of the other side. So it starts at the vertex of a triangle and then it connects to the midpoint of the other side. So what we're going to do is draw the median from vertex A to side BC in each triangle. So let's add that in here. It's to BC in each triangle. And then we're going to use tick marks to indicate that it is a median. So if this triangle, this yellow one right here, was actually in front of me, what I would do is take a ruler and I would find the middle of BC. Or what I would do is take, if this was on a piece of paper, I could fold C onto B, and when I line up those vertices, I would find the midpoint. So here I have to more or less eyeball it. Let's say it's right there, and I'm going to call it M for midpoint. So the median would be this segment. It connects from A to M. The way that I would show in the picture that that's a median is that these pieces of BC get split exactly in half, and I put tick marks there to show that BM is congruent to CM. All right, looking over here at the pinkish purplish triangle, if I wanted to draw the median from A to BC, I would find the middle of BC. I can't do it on an iPad screen, so I'm just gonna eyeball where I think it would be. I'm gonna put 2 tick marks to indicate now that CM is the same length as BM, and then to draw the segment, I have to connect it to the vertex. Now, keep in mind, every triangle has 3 different medians. I was only asked to draw the one from vertex A. I could have been asked to draw the median from vertex B, and if I did that, I would find the middle of CA. Again, if I had to eyeball it, let's say it's right there, let's call it point Q or something, and then that would be that median. And then, of course, I could draw the third one from C to BA. I would find the middle, let's call it Z, and then I would connect those segments. Okay, we're only being asked to draw one. And I realize now that I completely skipped over the first one. So why don't you kids do the blue one on your own? Draw the median from vertex A to segment CB. And draw the tick marks to indicate that it is a median. Okay, it should look something like what I have here in green. Okay, so the next segment that we're going to talk about today is the altitude. And altitude is also from a vertex, but it's going to be perpendicular to the opposite side. It can also be called the height of the triangle, and in which case the opposite side would be called the base. So everyone knows, like, you use base and height of triangles with area and stuff like that. So now we are going to be drawing the altitude. Okay, and it can also be drawn from any vertex in a triangle. Sometimes the altitude is going to be on the outside of a triangle, as we will see in a second. All right, so looking at the yellow triangle here, we're going to draw altitude from vertex A. So I have to start at A, and then I'm going to just take this segment and drop it down to the opposite side. Where it intersects the opposite side is not important. Doesn't have to be in the middle. It doesn't have to split it in some sort of special way. It's just a segment from the vertex to the opposite side along a perpendicular. All right, if I was to do that here in this green triangle, it would be, let me maybe do yellow. I'm, again, kind of eyeballing it because it's difficult on this app that I'm using, but it is going to intersect the other side and be perpendicular to it. That's it. It doesn't split it in half. It doesn't do anything else extraordinarily special. For the blue triangle, here, if I drop A from A to the opposite side, the only way that that can happen is that altitude is going to have to be on the outside. And so we kind of extend this base of BC, we extend it, and then the altitude is found outside the triangle. And here in triangle, the purple triangle, if I drop an altitude from A to the opposite side, again, I'm kind of eyeballing it. I want it to more or less hit at a 90-degree angle. And there's where that altitude would be from A. Now, in this right triangle, I want you to think about two other altitudes, because remember, an altitude can be from any vertex in the triangle. So here, for example, if I did from vertex C to the opposite side along a perpendicular, it would be right there. From B, it would be more or less there. And I can't straighten out my line so it doesn't look fantastic, but that's where the other vertices or the other altitudes would be. Okay, so in this one, where would the other altitudes be? Let's consider starting at vertex B. If I wanted to drop an altitude from vertex B to the opposite side, notice what would happen is the segment I'm drawing, would you look at that? It's the leg of the right triangle. Let's look at an altitude from C to the opposite side. If I drew it from C to the opposite side, it's the other leg. And so therefore, in every single right triangle, two of the altitudes are the legs of the triangle. Every single time. So the leg could be a height, and then the other leg would be the base. And then if you flip the triangle, same would be true. They could switch names, right? If I flip this triangle, the height could be CA, and then the base would be AB. Okay, next one we have is an angle bisector. An angle bisector is a segment that also goes through the vertex. So far, every segment that we've had has to start at the vertex, and it's going to be one that bisects the angle. And it can be drawn from any vertex in the triangle. So we're only going to focus on one for each of these again. We're going to focus on the angle bisector from vertex A. So when I draw that angle bisector, what I'm going to do is I'm not going to draw it like this, because that doesn't look like it split the angle in half. Instead, I'm going to try to be careful and more or less, and it's, again, on notability a lot easier when you have the strengthening or straightening line tool. So here, again, I'm kind of eyeballing it, but I just split that angle in half. Notice there's nothing special happening over here. It doesn't intersect perpendicularly. It doesn't intersect the other side in a special location where it's halfway through. There's nothing about how it intersects the other side that is significant. Okay, it's always just what's going to happen is it splits that angle in half. All right, so for the purple triangle, let's try to draw an angle bisector. So I start at A, and I'm more or less drawing a segment from there that is going to split this angle into two equal pieces. And the way that I show that, again, is my arcs. In this purple triangle, I did a double arc for each of them. In this green triangle, I did a single arc, but that is showing that the angle gets bisected. Those are the tick marks that I had to draw, or the arc marks. Now finally, let's look at this right triangle. If I draw the angle bisector from the right angle and I split this into two equal pieces, here I actually know what these angles are. They would be 45 and 45 from this angle. How is that true? How do I know that without a doubt? Because if I'm bisecting a 90-degree angle, a right angle, half of 90 is 45. So that's how I knew that those two were 45. Here, I had no way of knowing what those two angles were. Unless I gave you angle A, then I could find what each one is. Or if I gave you a half of it, you would know what each angle is. But the right angle, when I split it, is definitely 45 degrees each. Okay, and the last segment we're going to talk about is a perpendicular bisector. A perpendicular bisector is a segment, line, or ray that is perpendicular to a side of a triangle at the midpoint. Now here's what's important. It does not have to go through a vertex, and it can be drawn to any side of the triangle. So again, perpendicular bisector is the only one that is not necessarily through a vertex, but here's what is important. It has to be perpendicular to the side, and it has to go through the midpoint. Those two conditions have to be met. So let's take a look at the blue triangle here. If I wanted to draw the perpendicular bisector of CB, I would find the middle first. And so I would put a dot where I think more or less the middle is. And because I'm calling that the middle, these two segments become congruent, and I show that with the tick marks. And now I would draw a segment, line, or plane, and it is important that I intersect that side at a 90-degree angle. Now this one, if I was to extend it, it does look like it's going to go through the vertex. And we're going to talk about that in a second, about isosceles and equilateral triangles with these segments. Okay, what about here? We want to draw the perpendicular bisector to side BC. So if I was to do that, I'm going to more or less find the middle of BC. So right about there looks good. This segment's going to be congruent to this one, and now I'm going to draw what appears to be a perpendicular line, or segment, or ray. I like to do lines though. Okay, and over here in the green triangle, again, find the middle. This looks like a lateral triangle, so just keep that in mind. And now, when I draw a segment that's perpendicular, whoa, looks like I did go through that vertex. So sometimes the perpendicular bisector goes through a vertex, but it absolutely does not have to. The other three segments we've talked about today have to go through a vertex. The median has to. It's vertex to midpoint. The angle bisector has to. It splits the angle in half, so it has to go through the vertex. And then the second one we talked about was altitude, and that always starts at a vertex, and it's perpendicular to the opposite side. All right, so let's take a look here at this yellow triangle, and it's an isosceles triangle ABC. We drew here median BM to the base AC. So if I know that this is an isosceles triangle, I know then that AB is equal to BC because they told me the base is AC, which would mean AB and CB are the legs. And we've learned that the legs of an isosceles triangle are congruent. So now AB is 10 and AC, this entire side here, is 8. We want to find the length of BM. Okay. All right, so if AC is 8 and this is a median, what that means is each piece here has to be half of 8 because it gets split in half, so it's 4 and 4. And then I also know that BM is congruent to itself. So these two triangles that the initial yellow triangle got split into are congruent because of side, side, side. So now that I know the triangles are congruent, I know all their corresponding parts are congruent. We learned that in the last section, CPCTC. Angle A is going to be congruent to angle C. I know that because of CPCTC, and I also know that because it's a property of isosceles triangles. I know this angle up here is congruent to this angle up here, and then this one down here is congruent to this one down here. Because these two are a linear pair and they're congruent to each other. Linear pair, they have to add up to 180. Congruent to each other means they each have to have the same measure. So 180 divided by 2 is 90 degrees. So instead of the little arc with the tick, I'm going to change this to a 90-degree angle. Now that I know that these are right triangles, I can find the length of BM by using Pythagorean theorem. Remember, Pythagorean theorem works when you have two lengths of a right triangle. You take the leg, square it, plus the second leg, you square it, and it's going to equal the hypotenuse squared. So let's work through this and see what we get for BM. 4 squared is 16 plus BM squared equals 10 squared is 100. BM squared is going to equal 84. And now we have to square root both sides and simplify the square root of 84. What perfect square factor goes into 84? 4 does. How many times? 21 times. Square root of 4 is the is just 2, so it's 2 square roots of 21 is what we get for BM. Okay, I want you to notice something. In this triangle, we should have found out that BM, that segment when we drew it, it is not only a median. Because this angle ends up getting split, it's an angle bisector. Because it's also perpendicular to the opposite side, it's a perpendicular bisector because it also goes through the middle. And additionally, it would be the altitude. It starts at B and goes perpendicular to the opposite side. That is an altitude. So in an isosceles triangle, if you draw one of the segments from the vertex, it has to be from the vertex, then that segment ends up being all 4 of these special segments that we talked about today. Okay, so let's use the triangle congruency method again. You should be able to find each angle measure in triangle PHM and triangle SHM. So if PM is equal to 6, we are going to find the exact value of PH and HM. Okay, if this is an isosceles triangle, and they told me up here that this is median HM, that would mean this side is also 6. Well, if it's equilateral, if this entire side down here adds up to 12, every single side of this triangle is going to add up to 12. This side is congruent to itself because of reflexive property. So therefore, these 2 triangles, these 2 smaller triangles that are drawn are congruent by side, side, side. Okay, where I have 6, 12, and then the side that's congruent to itself. So they are congruent by side, side, side. Because they are congruent by side, 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 this angle is congruent to this angle. The ones down here are going to be congruent to each other also. Therefore, just like before, if they're a linear pair and they're congruent, they each have to be 90 degrees. And then this angle up here is congruent to this angle up here. It gets split in half. So what we have to do is find the exact value of pH. Got it. HM, how am I going to do that? Pythagorean theorem. So I would take the leg 6 squared plus the other leg HM squared plus the hypotenuse, or sorry, not plus, equals the hypotenuse 12 squared. Okay, so 36 plus HM squared is going to equal 144. Let's subtract 36. HM squared is going to equal 108. Let's simplify this because we're going to have to square root both sides to get HM to not be squared. And what perfect square goes into 108? Go ahead and try to find it and we'll see if our answers match. So pause the video and try to simplify square root of 108. All right, so I found that 36 goes into 108. So the square root of 36 is 6, and therefore we are left with 6 square roots of 3 because 108 is 36 times 3, so 6 square roots of 3. All right, now let's find all the angles in here. So in an equilateral triangle, all the angles are 60 degrees, right? Because it is equiangular, so if every angle has to be the same measure. In a triangle, the angles add up to 180. 180 divided by 3 is 60. So now, here, I know this entire angle is 60, so each individual one has to be 30 degrees. Another way I could have found that is if I think about this right triangle as a singular, its 3 angles have to add up to 180. So if this took up 90, right, the right angle takes up 90 of it. Don't forget that little shortcut. These 2 angles have to add up to 90. That's all that's left for the 2 of them to share. So if this one already took up 60 degrees, this one has to be 30 degrees. Okay, so that is it for these special segments. You're going to have to identify them from a picture. You're going to have to know properties of them and how to solve for certain angles and certain sides that you're given. Knowing which segment is drawn. So for the next class period, get ready to complete the 3.3 classwork. All right, thank you everyone for watching. Have a great day. Bye.